Now, before we touch tools, laptops, or fancy adapters, the first real skill in car hacking is knowing how to physically find the CAN bus. Now, this is not theoretical here. This is something you do with probes, multimeter, and a little bit of patience. Now, the CAN bus is actually very easy to spot once you know what to look for. And at rest, both the CAN high and CAN low sit about 2.5 volts. Now that is your baseline. So when data is transmitted, CAN high jumps up to 3.5 volts and CAN low drops to around 1.5 volts. Now they move in opposite directions, and that differential signaling is what gives the controller area network its noise resistance. And now we are going to slow things down and do this properly. Everything we discussed about the CAN voltages becomes real here. Now, this is not a theory anymore. This is exactly how I teach engineers when they first touch a live vehicle bus. And on the screen, we will go to our tactics, techniques, and procedures lab. Here, I have published a new lecture. Maybe you can also read it from it. But if you are watching this lecture, you will learn more from this lecture here. Now you can see our lab here, our interactive lab you can see on the screen. Now you can see this interactive lab demonstrates how controller area network uses differential voltage signaling to represent logical state. Now you will actively manipulate the bus and observe how voltage levels translate into dominant and recessive bits. Now on the screen, you are looking at the live CAN bus lab. Now think of this as your virtual back probe and oscilloscope combined here. You can see. This is the oscilloscope here, the digital oscilloscope you can see. Now, you are going to manipulate the bus and watch how the physics of controller area network bus can actually behave. Now, controller area network works because of the differential signaling, as I have explained in previous lecture. Now, not because of magic, not because of software or anything, like because of voltage relationship, the CAN high, CAN low, and we can see the differential here, the difference between the CAN high and CAN low. And that's why it's called differential signaling. Now, before touching anything, look at the live bus voltage monitor here. You should see this CAN high, the CAN low. These are the equal, right? Differential is equal. Now, different voltage is near zero. Now, this is the idle state of a healthy bus. You can see the bus state, recessive idle. Now, you can see this is the idle state of a healthy bus. And now let's press the dominant pin here. Click. And here you can see immediately, you can see the CAN high here rise and CAN low fall. Now this is a dominant bit. Dominant always wins on CAN. Now this is arbitration in action. You can see the bus state is dominant, so it's active. And in any electronic control unit or engine control unit, asserting a dominant bit will override a recessive one, right? By the way, this happens in milliseconds, right? In the cars, okay? This happens in milliseconds. So, but we are slowing down here to understand better, right? And this is why attackers love CAN. And on the waveform representation, you can see the CAN high waveform and CAN low waveform as well in the dominant bit. But on the recessive bits, you can see they are both resting at 2.5 volts. And the dominant bit, the CAN high rises into 3.5 volts. 3.5 volts, you can see from the 2.5 volts. And CAN low drops all the way to 1.5 volt. And the difference is 2.0 volt. So if you are hunting through a wiring loom like this, you know, it's a twisted, it will probably and most likely be the twisted pair wire. So it will be very hard to, you know, organize and stuff, but you can still get it out. And so if you are hunting through a wiring loom and you see a wire, let's actually write our multimeter here as well. and you see a wire sitting steadily at 2.5 volts or fluctuating up and down by roughly 1 volt, your odds are you are very high that you are staring at the CAN bus here, right? And CAN wiring also comes in pairs. So always if you see a twisted pair like this together across the engine control units, sensors or modules, that should immediately raise your suspicion. And in the field, I usually ignore single wires unless I already know I am dealing with something exotic here. Now, now let's talk about the easiest access point, which is the OBD2 connector. On almost all modern devices, the CAN high pin is on pin 6 here, the CAN high, and the CAN low pin is on pin 14. You can see they are both the dark blue, right? And this is standard high-speed controller area network, also known as high-speed CAN. And this is usually where beginners start, and that is fine. But understand this clearly. Not all controller area network buses are exposed through the OBD2 connector. Many internal buses are hidden deeper inside the vehicle. So, getaway ECUs often isolate them intentionally, right? This is where wiring diagrams of your car becomes essential. And factory service manuals are gold. So without them, you are just guessing. And I have spent hours tracing internal controller area network lines behind dashboards because the bus I needed was never exposed externally. Now, this is normal work in a real vehicle research, but it's not that hard, right? And now let us shift to packet structure, because once you can connect to CAN, you will see traffic immediately, and it can be overwhelming. Now, there are two types of controller area network packets you will encounter: the standard and extended. But before explaining that, let's go back. We have covered the dominant bit here. Basically, the differential voltage increases, and this represents a logical zero on a CAN. And what about if we press the indirect noise? The CAN high sitting at 2.8 volts and CAN low sitting at 2.2 volts. Now, the differential voltage is 0.6 volt. Now, this here tells us something immediately. The bus is no longer clean. And at rest, both lines should be very close to 2.5 volts. And here, they split unevenly. Now, that means something is injecting interference onto the system. Now, let's look at the bus state. It explicitly says the noisy signal. Now, that is correct here. Now, despite the noise, communication is still possible. You may ask why? Because the controller area network does not care about the absolute voltage. It cares about the difference, the differential between the CAN high and CAN low. And right now, the differential voltage is still strong enough for receivers for reliably distinguish the dominant and recessive bits. And right now, the differential voltage is still strong enough, but in most cases, you will not see this enough differential here. It will probably, if the noise is too big, it will be probably 0.3 volts. And this is exactly why the controller area network uses differential signaling. Now, let's move our eyes to the wavelength representation. You can see the CAN high is oscillating and CAN L is oscillating in the opposite direction. Now, on your car here, if there's a noise, they will probably, mirror each other. Still, try to work, but if the differential is or the noise is too big, the differential will be little, right? And this is where you will get the communication errors between the vehicle components and controller units. And let's present the bus short fault, and let's say what will happen if there's a short on the bus. Now, the state right here is just completely hard failure. And it's worse than the noise, right? A noise, there's a chance that the CAN bus will still be able to communicate between the controller units. But when the bus is short, 99.99% of the time you will get the error, and the vehicle will just fail. Now, this is what the short to ground looks like on a CAN bus. Now, both lines have collapsed completely, as you can see. The receiver here sees nothing, and from the electronic controller units or engine control units point of view, the bus here has ceased to exist. And now look at the waveform representation. The CAN high is just a flat, and CAN low will be on just a straight line, right? And those X marks are important. They do not mean zero data. They mean just invalid, unreadable, and gone. And both lines collapse. Communication is no longer possible if the CAN bus is shorted. So no arbitration, no dominant bits, no recessive bits, and no error recovery, like when the controller units try to recover the errors from the noisy signal. They will fail here. And in a real vehicle, this condition triggers the immediate fault behavior, and the engine control unit will attempt retransmission. Now they will detect errors. Some will go just bus off, others will enter limp mode. Like for example, if there's a communication error on your, like I have experience with the BMW vehicles and some other vehicles as well. Now, when they enter the limp mode at the transmission control unit, there's a good chance that you will just stuck at the third gear. So there will be no upshifts or not the downshifts. It will be just start at the third gear, and the maximum speed, of course, will be limited. So that's basically what happens when the transmission, something internally in the transmission fails, or the communication between the transmission and engine control unit fails. And yeah, this will happen in the most of the vehicles. Or in the worst case, with the third gear, you can at least still get to some mechanic or go to your home. But most of the time, the vehicle just stop and it will refuse to go anywhere. And when diagnosing suspected CAN short to ground, disconnect nodes one at a time while monitoring voltage recovery. So the moment the CAN high and CAN low rise back toward 2.5 volts, you have isolated the faulty ECU or wiring segment. And this technique actually works faster than scanning the fault code and does not rely on any engine control unit being operational. So that is how you diagnose the faulty or shorted controller area network.